Okay, so this is a video of the notes from day 1 of gas laws, and we did some demonstrations of pressure, volume, and temperature changes in class, and I will put those demonstrations online for you to see if you want to watch some videos to kind of get an idea of those relationships. But before we kind of delve further into the notes, we need to talk about what specifically pressure is. So pressure occurs when a force is dispersed or exerted over a given amount of surface area. So pressure can be thought of as force per unit of surface area, okay? If you have a force acting over a very large amount of surface area, for instance, if you have skis, the amount of area of the ski that's in contact with the ground is large. If you divide force by a large area, then your pressure will be a low number. It will be a very low pressure. However, if you have a force that acts over a small area, in this case like an ice skate, and the blade of an ice skate, that's a very thin blade, so the surface area is small. This area here is very small. If you have force acting over a small area, so you divide force by a very small number, then the pressure is very large. Okay? So when we talk about gas pressure, specifically what we're talking about is the bombardment, and that means collisions, of gas molecules on the sides of a container in a certain amount of space. Okay? So if you look at this picture right here, in picture A, in the first beaker, the surface area, the volume of that beaker is large compared to the beaker on the right. So the volume is large, so the gas molecules in constant random motion are hitting the sides of the container, and they're causing a pressure. But if you decrease the area, if you decrease the volume of space for those gas molecules to be in, now not only are the gas molecules hitting the sides of the container, but they're hitting the sides of the container of a very small area. So this pressure is large. Okay? The less space, the less area there is for pressure to be distributed, the higher the pressure gets. Pressure is caused by the constant bombardment or collisions of gas particles over a given amount of surface area. If you have a large number of gas particles, molecules or atoms, and you pump them into a container, the pressure of the gas in the container will be high because there are lots of collisions between the gas particles and the sides of the container. So for instance, if I had, and we're going to pretend like these are identical containers, okay? If I had a container with 4 moles of gas, and then an identical container with 12 moles of gas, this container on the right will have a higher pressure because there are more moles of gas, which means there are more collisions, and the collisions cause the pressure. The container on the left will have a lower pressure because there are fewer moles of gas, and as a result there are less or fewer collisions. Okay? So the pressure is directly related to the number of moles of gas in the system and how many collisions there are. And it's also related to the volume or the area. Pressure can be increased by adding more moles of gas particles, which you just saw. If you increase the temperature of the gas, that will increase the pressure. Or if you decrease the volume of space in the container. And that decreasing the volume of space is shown by this diagram up here. If you decrease the volume from A to B, the pressure will increase. Now, in terms of the temperature, we're going to talk about how temperature relates to pressure on the next slide. Pressure can be measured in the following units, and these units, ATM is atmosphere, mmHg is millimeters of mercury, torr is another unit to measure pressure, and kilopascals is the final unit to measure pressure. And these equalities are all on your reference sheet. And in the How to Solve Gas Law Math Problems recording, I'm going to show you how to convert between those different units of pressure. I want to go back just a second. This picture right here is a diagram of a barometer. And a barometer is used to measure atmospheric pressure. So, if you're listening to a weather report, you're using barometers to say what's the pressure of the air in the atmosphere. So, in the dish down here, there is mercury. And mercury is a liquid metal. Okay? And what will happen is air from the atmosphere will press down on that mercury in the dish. And sitting in the pool of mercury, there's an inverted tube that's open. Okay? And the air pressure will push down on the mercury in the dish, causing the mercury to go up in the tube. And the mercury will rise to a column height that equals the force of the atmosphere, the pressure of the atmosphere. Okay? So the higher the outside pressure, the higher the mercury will rise in the column. And so when we say millimeters of mercury for a unit of pressure, we're really talking about what is the height of the mercury in this tube. Okay? So when you hear that term, that's where that's coming from. Right, next variable we need to discuss is temperature. Temperature, you definitely need to know its definition. It's a measure of the average kinetic energy of all the gas particles in a system. And it's the average. It doesn't mean all of the gas particles have that kinetic energy. It's the average energy of the gas particles in that system. So kinetic energy, I'm going to move down here. Kinetic energy, I'm going to abbreviate KE, is equal to 1/2 mass times velocity squared. So kinetic energy, the amount of kinetic energy is dependent upon what the mass of the gas is and its velocity, how fast it's moving. Okay? We're going to talk about that in just a minute. If you have two different samples of a gas at the same temperature, because temperature is average kinetic energy, that means they will also have the same average kinetic energy. And that's super important for you to understand. If two gases, even if they're different gases, are at the same temperature, their kinetic energies will be the same. But it does not mean that the speed or the velocity at which the gas is moving will be the same. So if you have two samples of a gas at the same temperature, the gas with the greatest mass will be moving with a slower velocity. The higher the mass, the slower the molecule or the atom. The smaller the mass, the faster the velocity. Okay? So here's an example of what you may see. If I have two balloons, and they're both at 80 degrees Celsius, one balloon contains hydrogen gas, The other balloon contains carbon dioxide gas. Both of these balloons are at the same temperature, so they have the same kinetic energy. But kinetic energy depends on mass and velocity. So if I ask, in which balloon are the molecules moving faster, what you need to do is say, well, the molar mass of hydrogen gas, H2, is 2.02 grams per mole. If I take the molar mass of CO2, that's going to be 44.01 grams per mole. So that would mean that the hydrogen is moving with a faster velocity because the mass is smaller. The carbon dioxide is moving with a slower velocity because its mass is larger. Okay? All right, it is super important for you to pay attention to this next bullet point. When we are solving math problems, specifically for gas laws, the temperature must be converted to Kelvin before you solve the problem. Temperature in Kelvin is found by taking your degree Celsius temperature and adding 273 to that. Okay? Temperature is also directly related to pressure and to volume. So, for example, if I were to take a balloon and I were to increase the temperature, that would cause the gas molecules inside of the balloon to acquire more kinetic energy. So they would speed up and they would spread out from each other, causing the balloon to inflate. So you'd have an increase in volume. Additionally, if I were to take, and don't ever do this, but if I were to take a metal can with gas in it, and I were to heat that can, the gas inside the can would gain kinetic energy, and as a result, it would start hitting the sides of the container with greater force. And those collisions cause pressure. And more collisions with greater force equal a higher pressure. So eventually, this can would have so much pressure inside that it would explode due to the buildup of pressure. So what I want you to see is that volume and temperature are directly related. If one goes up, the other goes up. If one goes down, the other goes down. And same thing with pressure and temperature. Temperature goes up, pressure goes up. Temperature decreases, pressure decreases. Okay? Okay, so the next thing we're going to talk about is how gases move from one area to another area. And I'm sure in biology you talked about concentration gradients and transport. So this is somewhat similar. So there are two terms that both result in a net movement of gas molecules or particles or atoms, but they're slightly different in what specifically is happening. So we have diffusion and effusion. Diffusion means, think about perfume. If you were to come into a room and spray perfume or cologne or air freshener in one area of the room, eventually another area of the room opposite of where the substance was sprayed, you'd be able to start smelling the fragrance. So diffusion is the mixing of gas molecules that occurs just by random motion under conditions where molecular collisions can occur. So if you have a sample of gas on the left here and a sample of gas on the right here, and you allow them to mix by sort of a concentration gradient, the gas on the left or the gas on the right will diffuse to the left and vice versa. And that's just going to occur naturally and randomly. If you bake a pie or you bake cookies and you start to smell that in another part of the house, that happens because of diffusion. The fragrance is carried on the air molecules throughout a space just due to the random motion of the gas molecules. Effusion is an escape of a gas molecule through a very tiny pinhole opening without molecular collisions. Okay, so the gas isn't carried by air molecules, it just moves on its own, it moves naturally. Okay, so you have a pinhole opening and the gas is able to escape through that pinhole opening. Think about if you get a hole in your tire, or if you pop a small opening in a balloon and you hear the air hissing out of that, that is effusion. In general, the rates of diffusion and effusion are directly related to the average velocity of a gas particle. The faster a gas is moving, the faster a gas will diffuse, and the faster it will effuse, the faster it can escape. And gas particles with higher average velocities will diffuse and effuse faster than those at lower velocities. If you have two gases that are at the same temperature, the gas with the greatest molar mass will diffuse and effuse more slowly because mass is related to velocity. If your mass is high, the speed of the molecule will not be as fast as a gas with a lower molar mass. So I wanted to show you a short clip. So this is probably not going to work. Hang on. So what I'm getting ready to show you is an example of diffusion. This is bromine gas, and it's sort of an orange-colored gas. And we're going to watch how it diffuses from one part of a cylinder to another part of a cylinder.
In the lab, using bromine, an orange-colored gas. Place a jar of air on top of the bromine, and it slowly starts to spread. It's moving up the tube against gravity. Over time, the two gases mix. After half an hour, both containers have a uniform color. It takes time because the air and the bromine molecules are colliding with themselves and each other. So what would happen if there was no air for the bromine to bump into? All the air has been removed from this apparatus, apart from the flask containing bromine, which is isolated by a tap. Open the tap, and it spreads immediately. Watch again. In a vacuum, there's no air to collide with. The bromine diffuses much faster. See how slow the diffusion is when the flask is now full of air. It takes several minutes to get just this far. This simple setup can be used to compare the rate at which different gases diffuse into air. Nitrogen dioxide gas on the left is similarly coloured to bromine on the right, but bromine molecules are much heavier. The lighter nitrogen dioxide diffuses more quickly.
Okay, so you can see how molar mass is related to the speed or the rate of diffusion. The heavier the mass, the slower it's going to diffuse. Okay, so the next thing we need to talk about is a gas law that doesn't get looked at a lot, but it's really very simplistic, and it's kind of cool, and it makes sense. Avogadro's law, and this is your same Avogadro who came up with your Avogadro's number. Avogadro's law relates volume of a gas and moles of a gas. And what I need you to understand is that volume does not mean how much gas. Volume means how much space a gas takes up. Moles mean how much gas, how many particles. Volume does not mean that. Volume means how much space does the gas take up. Avogadro's law says that the volume of a gas, the amount of space it takes up, is directly related to the number of moles. So that means if I have 1 liter of volume, then I have 1 mole of a gas, for instance. If I were to double that volume to 2 liters, then I would double the number of moles to 2 liters. The more moles of gas you have, the more space the gas will take up. If you look at this example over here, if you have half a mole of gas, the balloon is very small. If you quadruple the moles of gas from half a mole to 2 moles, the balloon grows to 4 times the original size. The number of moles is directly related to the volume. This also becomes important because if I look here, I have helium, oxygen, and radium, okay? If all of these balloons are at the same temperature and pressure, and they all have the same volume, volume is directly related to the number of moles. So if all of these balloons have the same volume, then they all have the same number of moles of their respective gases. So for instance, if I have 5 moles of helium, because all of these balloons are the same volume, temperature, and pressure, then I would also have 5 moles of oxygen gas and 5 moles of radium gas. Okay, that's extremely important that you understand what that means. So I have some cartoons here because sometimes you're more visual with learning. So Charles's law relates volume and temperature. So if the temperature is very cold, then the amount of space that's being taken up by these people representing your gas molecules, is small. They're huddled together. As the sun comes out and warms up the temperature, the people don't need to be as huddled as closely. They gain more energy, so they start to spread out. So the amount of space taken up by the gas increases. And when these people are hot, they're far apart from each other. They don't want to be close to each other. So you've got a much larger volume of space taken up. Charles's law says that as temperature increases, so does the volume. Or if you go the opposite way, as temperature decreases, so does the volume. Avogadro's law relates, if you remember, the number of moles of a gas to the volume of the gas. Number of moles to the space that the gas takes up. So if you just have 2 bunnies, those are your moles of gas, they don't take up a lot of space. If you add more bunnies, because bunnies multiply quickly, then they're going to take up more space. And then finally, if those bunnies keep multiplying, you have lots and lots of bunnies, they take up a large amount of space. So that is Avogadro's law. And then the last one, Boyle's law. Boyle's law says that as pressure increases, the volume decreases. So you've got some gas molecules, they're not under much pressure at all, they're happy, they're good, they're spread out. As the pressure, the external pressure increases, those gas molecules start to compress and get closer to each other, so the volume decreases. And as the pressure increases even more, the volume decreases by the same factor. This is an inverse relationship, and this is the only gas law that has an inverse relationship. I'm going to pause right here, and I'm going to do another video for you where I go through and explain these review questions, but that'll be posted later after your homework is due.